ChatGPT confidently told someone that the Golden Gate Bridge was built in 1892? It was not. The bridge opened in 1937, but the model had no way to check. It just guessed based on patterns. Now imagine that same confident wrongness applied to your company's legal documents, medical records, or financial data. Terrifying, right? But here is the thing. There is a technique that fixes this. It lets any language model look up real information before answering, almost like giving it an open book exam instead of forcing it to rely on memory. It is called Retrieval Augmented Generation, or RAG. And by the end of this video, you will understand exactly how it works and why every serious AI application is using it. Language models have a fundamental limitation that most people overlook. They can only use information that was baked into their weights during training. Ask GPT about a paper published last month, and it has no idea. Ask it about your company's internal wiki, and it will make something up rather than admit ignorance. This is not a bug. It is how these models work. They are pattern completion engines, not knowledge retrieval systems. And that distinction matters enormously when you need accurate, up-to-date, or private information. RAG stands for Retrieval Augmented Generation. Let me break that down. Retrieval means finding relevant information from a knowledge source. Augmented means we enhance or add to something. Generation is the language model producing an answer. Put it together, we retrieve relevant documents, augment the prompt with that context, then let the model generate a response. The model is no longer answering from memory alone. It is answering based on evidence you provide. Every RAG system has two distinct phases. The offline phase happens before any user asks a question. This is where you prepare your knowledge base. You take your documents, split them into chunks, convert those chunks into embeddings, and store everything in a vector database. Think of this as building the library and creating the index card system. The online phase happens at query time. The user asks a question, you search for relevant chunks, stuff them into the prompt, and get an answer. The offline work makes the online search possible. Here is where the magic starts. An embedding is a way to represent text as a list of numbers. Usually 384 to 1536 numbers depending on the model. But these are not random numbers. They capture the meaning of the text in a way that similar meanings end up as similar number sequences. The sentence, "The cat sat on the mat," and "A feline rested on the rug," have completely different words, but their embeddings will be very close in this number space. This is called semantic similarity, and it is the foundation that makes RAG work. Embedding models learn by seeing billions of examples of text used in context. When words appear in similar contexts, they develop similar representations. The word king minus man plus woman famously equals something close to queen in embedding space. These relationships emerge automatically from training data. Models like OpenAI's text embedding IDEA or open source options like BGE and E5 have learned remarkably nuanced semantic maps. They know that debugging code and fixing software errors mean the same thing, even though they share no words. Once you have embeddings, you need somewhere to store and search them efficiently. That is what vector databases do. Options like Pinecone, VV8, Milvus, and Chroma are purpose-built for this. They use algorithms called approximate nearest neighbor search, things like HNSW or IVF, to find similar vectors without comparing against every single one. This is critical. If you have 1,000,000 document chunks, you cannot compute 1,000,000 similarity scores for every query. These databases make billion-scale search happen in milliseconds. Before embedding documents, you must split them into chunks. This sounds simple but gets tricky fast. Chunk too large, and your embeddings become vague averages of too many topics. Chunk too small, and you lose context. A paragraph about it means nothing without knowing what it refers to. Common strategies include fixed size chunks with overlap, splitting by sentences or paragraphs, or recursive splitting that respects document structure. There is no universal right answer. A legal contract needs different chunking than a technical manual. You will likely experiment with multiple approaches. When a user asks a question, the retrieval phase kicks in. First, the question itself gets embedded using the same model you used for documents. This is crucial. You cannot mix embedding models. Then the vector database searches for chunks whose embeddings are closest to the question embedding. Closeness is typically measured by Cosine similarity, essentially measuring the angle between vectors. The top k most similar chunks get returned, usually somewhere between 3 and 10, depending on your context, window, budget. These chunks are your retrieved evidence. Cosine similarity deserves a quick explanation because it is everywhere in RAG. Imagine two arrows pointing in 3D space. Cosine similarity measures the angle between them, ignoring their length. If they point the same direction, the cosine is 1. Perfect similarity. If they are perpendicular, it is 0. No relationship. Opposite directions give negative 1. In high-dimensional embedding space, this same principle applies. Two chunks about machine learning will have a small angle between their embedding vectors, even if one is longer, because it has more text. The direction carries the meaning. Now comes the augmentation step. You take the retrieved chunks and inject them into your prompt to the language model. A typical pattern looks like: answer the following question based on the provided context. Context: chunk 1, chunk chapter 2, chunk chapter 3. Question: user question. The key instruction is telling the model to use the context, not its memory. Some prompts explicitly say, if the context does not contain the answer, say you do not know. This grounding instruction fights hallucination. The model now has real evidence to work with. With the augmented prompt ready, the language model does what it does best: generate fluent, coherent text. But now, it is not pulling from fuzzy training memories. It is reading the actual context you provided and synthesizing an answer. Good RAG responses often reference or quote the source material. Great RAG systems even include citations, telling users exactly which chunk supported which claim. The generation quality depends on your base model, but even smaller models perform remarkably well when given the right context. Pure semantic search has a weakness. It can miss exact keyword matches that matter. If someone searches for error code E4501, semantic similarity might not rank documents containing that exact code highest. Hybrid search combines semantic search with traditional keyword search like BM25. You run both, then merge the results using techniques like reciprocal rank fusion. This gives you the best of both worlds: semantic understanding and keyword precision. Most production RAG systems use some form of hybrid search because the real world demands both. RAG is not magic, and it fails in predictable ways. Retrieval failures happen when relevant chunks exist but are not retrieved. Bad chunking, wrong embedding model, or poorly phrased queries cause this. Context stuffing problems occur when you retrieve too many chunks and overwhelm the context window, diluting relevance. Lost in the middle is a documented phenomenon where models pay less attention to information in the middle of long contexts. And reasoning failures happen when the model has the right context but draws wrong conclusions anyway. Knowing these failure modes helps you debug. Several techniques can boost your retrieval accuracy. Query expansion takes the user's question and rewrites it multiple ways to catch more relevant chunks. High DE or hypothetical document embeddings generates a fake answer first, then searches for chunks similar to that answer. Re-ranking uses a more expensive cross-encoder model to rescore the top candidates after initial retrieval. Metadata filtering lets you narrow search by date, source, or category before vector search even runs. None of these are mandatory, but each can meaningfully improve results when basic RAG falls short. Building RAG for real users adds complexity. You need evaluation metrics. Are retrieved chunks actually relevant? Do generated answers match ground truth? Latency matters because users will not wait 3 seconds for every response. Cost scales with embedding model calls and LLM tokens. You must handle document updates. When source material changes, embeddings need refreshing. Guardrails against prompt injection become critical when user queries interact with retrieved content. And monitoring is essential to catch drift in retrieval quality over time. RAG in production is a system, not just a prompt. A common question: should you use RAG or fine-tune your model? They solve different problems. Fine-tuning changes how the model behaves, its tone, format, or reasoning patterns. RAG changes what the model knows without touching its weights. For most knowledge-intensive applications, RAG is the right choice because you can update information without retraining. Fine-tuning makes sense when you need consistent stylistic behavior or specialized reasoning. Many production systems use both. A fine-tuned model for behavior, RAG for knowledge. They are complementary tools. Ready to build? Start simple. Pick a small document collection, maybe 10 PDFs or 100 pages of text. Use LangChain or Llama Index, which abstract away much of the complexity. Choose a hosted vector database like Pinecone or run Chroma locally. Use OpenAI embeddings if budget allows, or an open source model like BG Small. Build the basic pipeline, then iterate. Add better chunking. Try hybrid search. Implement re-ranking. Every improvement compounds. The best way to understand RAG deeply is to build one, break it, and fix it yourself. Let us recap what you now understand. First, RAG works by retrieving relevant documents and injecting them into prompts so language models can answer from evidence, not memory. Second, embeddings are the key technology that makes semantic search possible by converting text meaning into searchable numbers. Third, production RAG requires careful attention to chunking, retrieval quality, and system monitoring. Next, watch our video on building a complete RAG pipeline with Python. We go from zero to working system in under 20 minutes. If this breakdown helped you, hit subscribe so you catch that tutorial. And tell me in the comments, what documents are you planning to make searchable with RAG? Your company knowledge base? Research papers? I want to hear your use case.